compact case. Of course, there will be a lot of problems associated with non-compactness. So the existence of at least one periodic geodesic on compact manifolds, that of course is a well-established fact. It was proven by Lusternik and Fett. And so it's not the existence that we worry about when we talk about compact case, but rather we are interested in the following two questions. So this is first question by Bunkers. Here's question 2. This is a question due to Gromov. And he asked, is there a constant such that the length of a shortest periodic geodesic on a closed Riemannian manifold, which I will always denote now as this. On a closed Riemannian manifold. Is bounded above this constant times nth root of volume. And then there is a similar natural question, but in terms of diameter rather than volume. The length of a shortest periodic geodesic is bounded in terms of the diameter. Okay, so those are sort of the questions from which I began my research. And well, okay, let me first of all say that the answers to those questions are known in dimension 2. So dimension 2. Well, everything is, you know, all the answers are positive. So, so the answer to the first question was sort of obtained in steps. First, Thorbergson proved the existence of a periodic geodesic on surfaces with at least 3 ends. Okay, and then Victor Bongert, he dealt with a more complicated case of no more than 2 ends. So he dealt with situations, well, something like this. Or something like this. So if they obtain the answers to question 1. Now, question 2 and 3 are also quite a bit easier in dimension 2. So if a manifold is not simply connected, then the bound, you know, the length of a shortest periodic geodesic is bounded by twice the diameter. That's actually a very easy fact that I'm not going to dwell too much on. But the area bounds still were found in dimension 2, starting from the results of Lervner, who obtained it for 2 torus and Pew. For RP2, well, Riemannian RP2, right, with arbitrary metric, of course. And the most difficult case here is the case of a Riemannian 2-sphere. So the case of Riemannian 2-sphere, the first bounds were due to Croak. Then they were also kind of improved in stages, first by Maeda, then independently Alex and me and Stefan Sabouroux, so jointly with Alex but independently from Stefan Sabouroux, we improved those bounds. So we improved those bounds to 4 times the diameter and 8 times square root of area. Okay, and later even I improved it a little bit to 4 square root 2 square root of area. Actually, there is something here that I would like to prove later. Okay, so I would like to prove this bound later because the method is going to be suggestive of how we approach proving the theorem that I stated right here. And it's going to be much easier to present. It's not going to be quite the method by which it was proven at that time, but I found myself sort of, going back to thinking about sphere because those are not sharp bounds. And every time I think about it, I come up with a new method of proving 4D, but nothing better than 4D somehow. So, right, so now what about higher dimension? So higher dimensions, we don't have much. There is a bound by Gromov, of course, that holds for a wide class of manifolds that are called one-essential manifolds. Well, for example, those include RPN or manifolds that admit metric of non-positive sectional curvature. But if we try to apply various methods to, so what we want, right? I mean, what we want, it is curvature-free upper bounds for the length of the shortest periodic geodesic. But instead, what we can possibly get, I mean, like I tried it, and I tried it with some courses, and our students tried it. So what we can get is either curvature-free, but not for periodic geodesic, or it's for periodic geodesic, but involves curvature. So let me state right away the bounds that involve curvature. That's not something I want to focus on, but because the last result is kind of recent, was obtained by our students, I would like to at least state it. So the bounds involving curvature. So the first general bound was obtained by Alex and me. And it was for the class of manifolds. I'm going to denote it like this. So this is M, K, V, D. This is a class of manifolds with curvature bounded from below, a volume from below, and diameter from above. And the reason that we could obtain the bound for the length of the shortest periodic geodesic was the fact that, well, due to Grove and Pearson, we have a contractibility radius on those manifolds. So this is essentially what we used. Now, recently, our students, so Nan Wu and Jifei Zhu, obtained the following result. Okay, so, well, maybe I'll write it here. So this is a theorem that is due to Nan Wu and Jifei Zhu. Okay, so let M be a closed Riemannian manifold. Of dimension 4 with bounded Ricci curvature. volume bounded from below and diameter from above. Then there exists a function that depends on volume and diameter, such that the length of a shortest periodic geodesic can be bounded in terms of this function. Okay, and the way they have obtained the proof to this theorem is by using recent work of Chigger and Neighbor, the structural theorem that gives neck and body decompositions of a manifold with Ricci curvature, with bounded Ricci curvature. Okay, so moving to the curvature-free bounds. So one of the first bounds was actually due to Stefan Sabro, and that was for the length of a shortest geodesic loop. That does not have to, on the whole manifold, doesn't have to be a periodic geodesic. There are examples when this is not the case. So he found estimates of the length of a shortest geodesic loop. So he found that there is a bound in terms of volume. And he also found the diameter volume. Length of shortest geodesic loop. Why did I maybe SGL? That makes more sense. Thank you. So he found diameter bound as well. So this is Stefan. And at about the same time, Alex and I obtained bounds on the length of a shortest geodesic cycle. So I will describe those results in a little bit more detail. So maybe let me leave this theorem here. Okay, so stationary geodesic cycles. Those are geodesic nets that are also cycles. And let me just remind you briefly what the geodesic nets are. I mean, Alex discussed them last week, but it's going to take, I'm going to briefly give the definition, right? So geodesic nets, those are graphs, multigraphs. Each edge is a geodesic. And at each vertex, you have a stationarity condition that if you look at the unit tangent vectors that are emerging out of the vertex, at each vertex, their sum is equal to 0. So those are critical points on the space of graphs of the length functional, length or energy functional. Now, so why do you possibly want to study geodesic nets? I mean, they're quite basic objects. There are not too many of those. But also sometimes those methods, when we study geodesic nets, they actually do lead to the, well, I have to say seldom, but actually do lead to the bounds of periodic geodesics. One can also sort of study them as an object that naturally generalizes to minimal surfaces in higher dimension. Okay, so geodesic nets are something like this. Of course, periodic geodesic is a geodesic net. example, can consider a theta graph on a sphere. So you have 3 geodesics that join 2 vertices, and they make angles of 120 degrees. So this is also an example of a geodesic net that is not a periodic geodesic. So quite a while ago, with Alex, we obtained the following. That the length of a, so this is the length of a shortest geodesic cycle can be bounded by some constant times nth root of volume. And also in terms of diameter. And later on, I improved this result to the following.
What do you mean by cycle?
So it's a geodesic net that also is a cycle from topological point of view. Yeah. So, okay, so I improved it the following. I'm actually going to write it like this. And I'll explain what I mean in a second. I'm writing this bound because it's particularly nice to write. Something like this. Okay, so I have bounded the length of particular geodesic nets. Those are geodesic nets that consist of one vertex. So those are geodesic flowers, I call them. They have one vertex and have a bunch of loops that come, that diverge from this vertex, that originate from this vertex. And of course, they satisfy the stationarity conditions that's needed, for this to be considered stationary geodesic net. So here we could not say much about the shapes, but here I pinpointed to this. I mean, so there's always going to be something like this on a manifold, possibly periodic geodesic, but it have to be that's bounded in terms of diameter, in terms of volume. Okay, so now probably is the time to prove this theorem for D. So this is when the methods that we use here become actually useful to obtaining the bound for a periodic geodesic. So here is a theorem. The length of a shortest periodic geodesic on a Riemannian two-sphere is bounded by 4 times the diameter. Okay, so the proof that I'm going to demonstrate, well, we call it a sort of a pseudo-filling technique. It was used by Gromov, well, a similar technique was used by Gromov to find his bound for essential manifolds. And I think it conveniently hides all the issues, becomes very short. So here is the proof. And this essentially is a proof that, well, I mean, we generalize to higher dimensions and adapt to a non-compact case to prove this theorem. Okay, so M is a Riemannian to sphere, so it's a diffeomorphic to the round sphere. So let's begin with the diffeomorphism from S2 to M. Okay, so this is a round sphere, and we map it to, I don't know how this M looks, but maybe it looks relatively nice like this. So we have this diffeomorphism. I'm going to attempt to extend this map F to D3. So first, let me triangulate this into really fine simplices. So the diameter of simplices in the induced triangulation is less than delta. And I'm going to triangulate the disk D3 as a cone over S2. And I'm going to try to extend the map F to D3. And of course, I should fail. And as an abstraction to this extension, I'm going to obtain a periodic geodesic, a short periodic geodesic. I know there is a periodic geodesic already. So the extension procedure is going to be adductive to skeleton. So let's begin with zero skeleton. In the zero skeleton, we just have one additional vertex. It's the center of the disk. I'm going to call it P. And I'm going to send the point P to any point whatsoever on my manifold. So that's done. Now, I have to say that nothing exciting is going to happen until the three skeletons. So in one skeleton, I have edges. So they're the ones that connect P, the center of the disk, to the vertices of the triangulation of the sphere. And here I have now P tilde and VI tilde. That's where the boundary of this one simplex goes. I'm going to connect this by a minimizing geodesic. It's bounded by, of course, diameter. And so now I'm going to go to skeleton. And there I have two simplices. So this is P, Vi, Vj. Once again, I know where the boundary of the simplex is mapped. So it's mapped to, well, I have the point P tilde. I have Vi tilde, Vj tilde. Those are connected by a very tiny edge of the length less than delta. Those P tilde and Vi tilde are connected by the curve of length bounded by diameter. Here as well. So everything is mapped to the curve of length bounded by twice the diameter plus delta. And I'm going to use some curve shortening. Well, I'm better fix a curve shortening on a sphere. So let's say I'm using Birkhoff curve shortening. So I mean, remember, so sort of like, I mean, if I have a piecewise geodesic curve, I'm just starting cutting off corners by small curves. Right, that's going on. So I'm using curve shortening, and I'm going to either converge to a point, or I'm going to get stuck on a periodic geodesic. Well, if it's I get stuck on a periodic geodesic, that's nice, and I obtain a short periodic geodesic. So the worst case scenario is that I do succeed in contracting this to a point. So far, there is nothing particularly interesting. So now I'm going to go to three skeleton. And this is somewhat more interesting, so probably we'll use the whole board for that. So 3 skeleton. Okay, so right, so now I have a 3 simplex. And once again, by induction, I know where the boundary of the simplex goes to, right? I mean, so I start with those simplices, the vertices vi, v tilde, vj tilde, vk tilde. Actually, I have this whole tiny simplex that comes from the triangulation of S2, right, as the image. Then I have my point P tilde. And first I join this by edges. Let me call them E1, E2, E3. Then I take each pair of those edges and use a curve shortening to contract it to a point. So I have something that has 3 tentacles here. Like, I mean, I have this sphere, right? And I now would like to construct a disk that has the sphere as its boundary. So actually what I'm going to do, I'm going to attempt to homotope the sphere to a point. And well, I would like to construct, so let me call the sphere actually S2 sub 0. I would like to construct a family of 2 spheres S2 sub tau that starts from the sphere and ends at some point. Okay, and this is the way I'm going to construct this 1-parameter family of spheres. I'm going to, well, actually, let me be a little bit, let me cheat a little bit here. I'm going to take, because this simplex is so small, I'm going to treat it as a point. It's just for convenience of explanation. In fact, I can put a point here and deform it to a point, and this is a technicality. So what I imagine is I have something like this. I have something that I build from one skeleton from a net by contracting each pair of curves. Okay? So I'm going to construct this 1-parameter family of spheres by first shrinking this net to a point. Okay? So I'm going to apply the length shortening for nets, okay, applied to this net consisting of edges E1, E2, E3. Either it gets stuck on a geodesic net or it contracts to a point. Okay? So there are a couple cases to consider here. So case 1, I am deforming this net. And it gets shorter and shorter until it becomes a point. And in the process, as I deform this to a point, I also, at each time tau, consider each pair of those curves and contract it using the curve shortening. And as I contract it using curve shortening, I obtain my family of spheres. Okay? Does it make sense? So this is my one parameter family of spheres. So in this case, I can extend to the 3 skeleton, which actually makes no sense. I mean, I should not be able to do this. So the case 1, when I am able to do it for each 3 simplex, is impossible. Okay? So now I know that for sure, when I contract this geodesic net, I have to get stuck on a stationary geodesic net. Okay? And the way those stationary geodesic nets can look like, well, maybe it can degenerate as I'm using the length shortening to a periodic geodesic. So case 2A maybe is that I get a periodic geodesic, and the length of a periodic geodesic that I get is going to be bounded by 3 times the diameter. Now, well, you know, it doesn't have to look like this. In fact, right, I mean, one edge can disappear during the homotopy. And what I can obtain is a stationary figure 8. But I am on a surface here, so if I use the stationarity condition at the vertex, that means that this is a self-intersecting periodic geodesic. So this is still a nice case. I still have a periodic geodesic. That's what I wanted to have. Still bounded by 3 times the diameter. And now here is another case which is a little bit unsettling. Say it again? Well, it's smooth. I mean, so, okay. So, yeah, I mean, so this is a geodesic that looks like this, right? I mean, so you start walking, and then you walk, and then you continue walking here, and then you come back, and then you continue walking here. So you do walk without a singularity, right? I mean, you have to change direction, okay? So,
Is the bound there actually 2D?
3D. The bound here is 3D because, you know, so we apply the length shortening for the whole net. And one edge can disappear, but its length, the other edges will inherit its length. I mean, we can only bound it by 3D. So the troubling case here is this, is, well, one can actually get stuck on a theta graph. Okay, so that's a possibility, and it's not something we want. Okay? But there is a simple remedy for this situation, and the simple remedy would be that let's not apply length shortening, but let's instead apply the weighted length shortening. Okay, so I have here edge E1, E2, E3, and what I will try to do now is not shorten the length of E1 plus length of E2 plus length of E3, but rather shorten the length of E1, so the weights are going to be 1, 1, and 2. That sort of is the same as if I consider taking this edge with multiplicity 2. So can I get now, is it possible for me to converge to theta graph? It becomes impossible, because if I look at the stationarity condition, well, let me just look at, so this is going to be vertex maybe Q1, and this is vertex Q2. So let me look at the stationarity condition at the vertex Q1. I have V1 plus V2 plus V3. 2v3 should equal to 0, right? That means that the cosine of this angle has to be 0. So really, either one edge has to disappear, or 2 edges should collapse together. So in fact, I cannot, if I apply the weighted length shortening, I cannot get a stationary theta graph. What I must now get is either a geodesic with no self-intersection, or geodesic with a self-intersection, a figure 8. Now, though, since I use this weight 2, the upper bound is going to be 4 times the diameter. So I did get that the length of a shortest periodic geodesic is bounded by 4 times the diameter. Okay, so I said that to prove this theorem, there are kind of 2 steps that need to be made. One step is we need to apply this method in higher dimension. Second is that we need to, well, I mean, we don't have to apply this particular method, but that's what we can do. Okay, and the second step is that we have to deal now with non-compact manifolds. So let me just say a couple of words about higher dimension. Okay, so just for a second here, let me consider a Riemannian sphere of dimension n. And let's suppose I imitate fully the procedure above. Well, first of all, let me say right away that I'm not going to get a periodic geodesic, because stationarity condition, when I use the stationarity condition at each vertex, if I'm not sitting on a surface, it doesn't mean that I obtain a periodic geodesic. In fact, I can imagine that I obtain something like this. So I take two loops. One loop sits in one plane, and the second loop sits in a different plane, and they share the bisector. Okay? So, well, one can imagine, you take those two loops and one sort of twist it, right? I mean, it's a stationary net, but it's not going to be a geodesic. That's where the flowers are coming from, actually. So what will happen, let's say, if you apply this with the following weights, if you apply the length shortening with the following weights, so it's 1a squared, a to the power m for some integer that's greater than or equal to 3. Then if you apply this to a geodesic net, to a net that is obtained from two vertices and a bunch of segments joined together, if you apply it to something like this, it will force each edge to collapse to a point, but it will do something else. I mean, it will also force one of the loops to become rather wide. In fact, the bigger the a I choose here, the closer this angle is going to become to pi. So I can obtain a bunch of those wide loops that I can make them arbitrarily close to pi. Unfortunately, however, and I was doing it in the hope, to perhaps get a periodic geodesic, a short periodic geodesic as a limit. Fortunately, here the length of those loops is going to grow, so it's not going to approach to anything. However, so the best you can get the upper bound for the wide geodesic loops. So you can get that the length of, let me see if I have, well, you can get something like this, right? That the length of a wide geodesic loop is bounded by, let me see, so C of n or you can get a similar bound in terms of volume. So you can get those upper bounds for wide geodesic loops, and will not, unfortunately, give us periodic geodesics. However, this method will still play in some corollaries to this theorem. So it will have some role, play some role. Okay, so finally, let me now discuss the proof of this theorem, at least somewhat. Okay, so you have, if you have an angle, so let's say you want a geodesic loop, so that its angle is greater than pi minus epsilon for some small epsilon. We can take A to be this. Okay. So let me sketch a little bit the proof of this theorem. Now let me give you some difficulties that this proof involves. So the first difficulty is that we would like to use this pseudo-filling technique, but when dealing with non-compact manifolds, there is nothing to fill. Okay, so well, at least at first glance, right? I mean, so So maybe this is our manifold. And first difficulty. We have no fundamental class to fill. Now there is a second difficulty. The second difficulty is that our proof is based on using some shortening flows, okay? However, we use a flow, a curve shortening process. Here, our curves or spheres might start escaping to infinity. So the second difficulty is that there is escape to infinity phenomenon. Now, well, maybe that's not exactly a difficulty, is that, well, our conjecture is that at least if a manifold satisfies the condition that we have stated here, that there is a periodic geodesic. In fact, the only thing we can get so far in the general case, is geodesic nets of certain shape, flower-shaped geodesic nets. Okay, well, okay, so let me define what we mean by locally convex sense. Okay, if there exists a hypersurface, it might have more than one connected component. It separates manifold into a compact part and end. And it satisfies the following condition. Instead of writing it, I'm just going to draw it, okay? So let's say this is our manifold. And this is a surface, hypersurface that separates it. What I want is that for any points that are close enough here, if I join them by a geodesic is going to lie in the end. It's not going to enter the compact part. Okay? So it doesn't make sense. So why do I want this condition? I want this condition, so actually there were some people who contributed to the study of geodesics on, let me write their names. So they contributed to the study of geodesics in a non-compact case. They specified some conditions, and those conditions, they were designed so that if a geodesic, so the curve, when you apply the curve shortening, cannot escape to infinity. What we want with our condition is actually quite the opposite. What we want is that if a curve escapes to infinity, it does not come back. Okay, so with the problem, we're dealing with the problem too in the following way. That if the curve leaves us, then goodbye, we are not interested in this curve anymore. Okay, so the people that contributed, Benchi and Giannoni. And more recent is Arcelli and Mazzucchelli. Okay, so I was really unsure about the number of these C's and L's. Okay, so this condition that we have here is really to deal with this problem. Now, in dimension 2, let me point out the following: that in dimension 2, we actually the finite volume implies this condition. So, in fact, in dimension 2, what we get is that it's a new proof of existence of a periodic geodesic. Okay, so how are we going to deal with the fact that there is no fundamental class to fill? Well, I mean, I think the natural way here is to consider a relative homotopy. Okay, so a relative homotopy of the manifold relative to the ends. Okay, so let me maybe just briefly describe the starting point of the proof or in dimension 2. So here is what we do in dimension 2. Okay, this is very roughly speaking because I'm kind of out of time. So let's start with our surface. Let's cut it by those surfaces right here. So we obtain something that's truncated. And now let's cone this over here. Okay? So now let's take now this whole manifold and cone it as well. And we are going to try to extend the map. And I'm actually, so far did not say which map, okay, but we are going to try and extend it to this cone. Obviously, we should not be, so the cone, everything is contractible, so we should not be able to extend it, okay? So that's going to be, so as an abstraction to this extension, we are going to obtain a periodic geodesic. Well, there are many problems that I've just said here because, well, first of all, I did not say which map we're talking about. And essentially, the map that we are talking about, although even that's not quite correct. I don't know to how much you did this. Okay, so let me wave my hands a little bit because it becomes kind of technical from now on. What I'm going to try to do is the following. I'm going to try and take those cones. And first, let me, I have the identity map essentially from this compact part to itself. Now, first, let me extend this compact part from this cone onto these cones, the cones over those surfaces, okay, to the manifold. The problem is that when I try to extend it, the curve might run to infinity. So really, to be precise, I need to compactify the manifold as well. So I'm going to then extend those cones. The cones are going to the map from the cones are going to be mapped to the ends of the manifold plus some point in infinity. I will then try kind of sort of extend that map to the cone over the manifold. Okay? Again, there are many problems with this construction as well. There is discontinuity when we look at, so the flow is continuous unless the curve converges to infinity, but there are some discontinuities there, so we have to be a little bit careful about this problem as well. Okay, I think, at the remaining 4 minutes, I will not be able to say much more, so I'm going to stop right here.